I'm now going to talk about some particularly important performance issues, and that's about load imbalance and granularity. So, in order to create a parallel program, in general, we have basically four steps to consider. We'd like to decompose the algorithm into tasks that are sort of concurrent, and then we want to assign these tasks to parallel sort of executors or threads, and then orchestrate this computation, which is the actual programming, and then finally map these threads or processes onto physical cores or different machines, parallel machines. So we're going to talk a little bit about sort of what happens when the tasks does not really match the hardware. So the tasks is a programmer-defined unit of computation. So this is sort of a generalization of the term task used in OpenMP. This is a much more general concept. To decompose a program or algorithm is the process of dividing the main computation into tasks. And there are many kinds of decomposition techniques, and we're really gonna use only data decomposition here and talk about functional composition. Recursive, exploratory, speculative decomposition are special cases of functional and task decomposition. But we're mostly going to talk about data decomposition here. Things to consider here are task granularity. How big are they? How much computation do each task represent? And then task assignment for load balancing. So let's talk about load balancing here. If a thread gets an uneven load allocated, you have a reduced efficiency. So parallel execution time is determined by the thread with the heaviest load. So the example to the right here, thread T1 here executes for the longest time, so the whole program execution time is totally dependent on T1 here. So if you find that your program exhibits this kind of behavior, break up the workload in tasks more and allocates the task more evenly. And you can basically do that in two ways, either through static load balancing before execution or dynamic load balancing during execution. For the example here, we can take the execution of T1 divided into two tasks, move the red part to thread 4. Thread 6 is also changed to and thread 5. And then when you've done this, you have a pretty balanced workload here. So some examples on how you can do load balancing in code here. Here is an example of an imbalanced code. So we have a for loop. That where the inner loop starts from the value I on the outer loop, and which means that the first iterations of the outer loop will have many more inner loop iterations than the latter loops. So if you just parallelize the outer loop with a normal Paragma OMP parallel 4, this code will have a load imbalance. Basically, if you plot the amount of work on each thread, and you have threads here, the first iterations will have a lot of work, and then I will have lesser, and so on. Okay? You can improve this statically by adding a schedule static with a chunk size of 1. So the default schedule here is typically a schedule where you take the for loop and divide it into the number of partitions equal to the number of threads. Here we partition it with one iteration each, which means that you have thread 0 here, thread 1, thread 2, thread 3, and if you have 4 threads, you begin again with this case. So if you have many iterations, the workload of each thread will be roughly the same. Not exactly the same, but roughly the same. If you still have few iterations, this will still be show load imbalance. And you can solve this dynamically by specifying a dynamic schedule, meaning that the runtime system will hand out iterations to the threads as they are executing. So typical techniques for static load balancing is some kind of data decomposition or graph partitioning if you're using other kind of data structures. And techniques for load balancing dynamically is using the OpenMP dynamic work sharing schedules, or using thread pool patterns such as OpenMP tasks or the Intel 6 Plus TBB and so on. So data decomposition for static load balancing means that you map data and tasks to threads and possibly cores before the execution starts, which means that you have to know which task you have. Static task generation, you can't dynamically generate tasks, and the task sizes need to be known in order to work well. And unless you have a very simple problem like the one we had before, the problem of optimal mapping is really hard. It's shown to be NP-hard, but there are some reasonable approximation scheme here. So if you have 1D arrays that you work on, you can partition them by blocks, or like here, or cyclic striped, or block cyclic stripe, where you have different chunks. So this is supported by OpenMP with the parallel for loops and the static schedule with a chunk size. So here is a static schedule without the chunk size. Here is static schedule with chunk size 1. Here is static schedule with chunk size 2. You can extend this to two-dimensional arrays or three-dimensional arrays and get similar kind of results. It's pretty straightforward, but can be tricky to do this. But even if you have non-contiguous data, you can partition it. For instance, if you have lists, you can have define sublists of discrete elements. If you have graphs, you can construct subgraphs. But there is, in general, some extra work of doing this. Data decomposition of arrays and matrices is more straightforward. You can do that by calculation of indices. Here you need to sort of go through the whole data structure before you can start working on it, and this extra work sort of needs to be worthwhile. With dynamic load balancing, you typically distinguish between centralized schemes or self-scheduling schemes. So in centralized scheme, you have a master that generates the tasks and distributes the workload to slave workers. Easy to program, but the master is prone to becoming a bottleneck. Self-scheduling is one. It's also sort of a kind of. It's centralized, but each worker decides when it's going to take work from a work pool. It works nicely for shared memory programming. The first one, master-slave, works also for message passing when you don't have a shared memory. Self-scheduling more or less implies that you have shared memory and the work pool is in shared memory. Both of these can be combined with chunk scheduling, which is equal to have static schedule with block cyclic data distribution. In chunk scheduling, you don't take just one task. You take a chunk of tasks, several tasks at once, and you can do this either having the same chunk size all the time, or you can do it with sort of guided, where you start with large chunks, and then when you have few tasks left, the chunk size automatically decreases here. So decentralized schemes work more or less the same, except that you typically try to do some kind of load balancing between. You have maybe local queues of work to work on, and then when you get you're out of work to do, you go to some other thread's work queue and steal work from them. So about chunks of tasks. This is also related to the task granularity. So the size in amount of work to do of a task is called granularity. It can also be calculated in terms of execution time. And it's more efficient to deal with coarse-grained tasks, large tasks, because you need to do less scheduling and more execution. But fine-grained tasks provide for better load balance, like in this example here. To the left, you show some blue tasks that are poorly load balanced. You can do some load balancing here, but it's still unbalanced. If you break it up to finer tasks, like in the red part to the right, it's easier to achieve a balanced load here. If you can, it's always better to do static task assignment if you get a decent load balance. And trade-off between scheduling overhead and load imbalance is not a good, easy one. Besides load imbalance and dealing with granularity, it's also important to understand issues of lock contention. So locks are used to get rid of data races, and locks are also used, for instance, in dynamic schedulers. So they can severely sort of limit the parallel performance. So lock contention occurs when cores wait on locks that are used by other cores or other threads. So in order to sort of find that this is a problem, you use tools. So, for instance, profilers typically find if you find that when you do profiling that the code spends a lot of time in blocked APIs, you have lock contention. Several ways to tackle this. You can refine your algorithm to have fewer locks. You can adjust your lock granularity to lock smaller data structures. Use application-specific locks, or preferably use lock-free data structures if possible. It's an inevitable artifact of parallelization, but it's something that you need to be aware of. So to conclude here, to create a parallel program, we do decomposition into tasks. These tasks are assigned to threads or processes, and then orchestrate the computation by programming, and then map to physical cores. But the important thing to remember here is that while all of these were important stuff to consider in parallel programming previously, for instance, mapping the threads to physical cores is typically now done automatically by the operating system. We don't really want to think about this. This is done automatically. Although later OpenMP4 has some provision of doing thread affinity, meaning that you tell the system to not move around threads. If your thread has started on one core, it should continue on that core. And assigning tasks to threads, there are also now means to do that more or less automatically by the combination of compiler runtime system like OpenMP tasks and similar things.